So let's do an example problem here, computing work. So we got an object. Let's say we have a block here that has mass 4.31 kilograms. I exert a force on it, and let's say I have a force of 14.1 newtons, and I do this for a total of 1.75 seconds. Now, if we assume this thing's free to move, that means when I exert the force on it, it's going to be accelerating this way, and when I'm done, it's going to move some distance x. So I want to find x. It's real simple. X is just 1/2 at squared. So all I got to do is find a. Well, a is easy because that's F over m. So that'll be 14.1 newtons divided by 4.31 kilograms. So that comes out to be 3.27 meters per second. And so X is going to be 1/2 times A, 3.27 meters per second, times the 1.75 seconds squared. So X is going to be equal to 5.01 meters. This thing moved under the force a distance of 5.01 meters. So work, which is going to be force times distance, is going to be equal to the 14.1 newtons times the 5.01 meters. So the work is going to be 70.6 joules. Okay. Now it's interesting, how fast is it moving at the end of it? Because we'll need that for the next part. So how fast is it moving at the end of it? Well, that's going to be V0 plus AT. So V0 is 0, such as acceleration times time. So that's going to be 5.72 meters per second. So now what I've got is, after I turn off the force, then this thing is moving at 5.72 meters per second. Newton's first law. If you don't apply a force, it keeps moving in a straight line. This has been always a sticking point whenever physicists watch sci-fi movies, and you have the spacecraft going through space, and they cut the engines and they slow to a stop. And no, they don't. If you cut the engines, they just keep going at that speed forever without changing. But let's say we want this thing to stop. Well, turning off the force doesn't make it stop. We have to apply another force to stop it. So let's say, just pick a number out of air. Let's say this is a 21 Newton force. It's in the opposite direction to motion. So if I say to the right is positive, the force is to the left, so it's a minus 21 newtons. And so we know that work is going to be force times distance. So we need to know the distance. Okay, so the distance is going to be V0t plus 1/2 AT squared. Okay, well, we know that the final velocity when it stopped is 0. That's equal to V0 plus AT. So we can do a little bit of algebra, find that T equals minus V0 over A. Plug that into this equation. Y'all have done this before. So X comes out to be equal to minus V0 squared over 2A. So A is going to be F over M. So A is a minus 21 newtons divided by, it's the same object, same block, so 4.31 kilograms. So that comes out to be a minus 4.87 meter per second squared. So X is going to be the 5.72 meters per second squared divided by, or negative, divided by 2 times minus 4.87 meter per second squared, and that comes out to be 3.36 meters. So the work is going to be equal to minus 21 newtons times 3.36 meters. So the work is a negative 70.6 joules. Okay, so we had this thing, we exerted a force on it, so we did a work of 70.6 joules to get it moving. And then as it's moving, we had to push on it, so we did a work of minus 70.6 joules to stop it. Okay, so starting and stopping, it was the work was plus and minus. So you had to do the same work to stop it as you did to start it. It's just in the opposite direction. So now Newton's third law, if we exerted a force on it to get it going, it exerts a force in the opposite direction. So that means that it did a minus 70.6 joules on whoever was pushing it. Okay, now as it's stopping, then you're exerting a force this way, but it's exerting a force that way. And so that means that it's doing a 70.6 joule work on the person that is trying to stop it. Okay, and so you look at this and we say, okay, equal and opposite, equal and opposite. So when you did work, you were giving it the ability to do work on something else. So one definition here is if you do work on something, you give it the ability to do work on something else. Thomas Young coins the term energy for this sort of ability to do work. Energy, sorry. So he used the term energy. And one definition, simplistic definition you sometimes see in elementary school is energy is the ability to do work, because if you don't put energy into something, you can't take energy out of it very easily. So it's got to have some kind of energy. Now, it might have some energy already before you put it in there, but unless it has energy, it can't do work because it has to lose energy. And that was the idea, that in this case over here, that energy went from the person pushing it into the object. Over here, energy went from the object into the person pushing back. And so you have a conservation of energy. So the total amount of energy in the universe didn't change. One person lost energy to get it going, and then it gave up the energy and pushed and gave it to somebody else. And so conservation of energy is a byproduct of this whole concept of work being an interaction, force times distance. And notice that these are symmetric right in here. And so this is something to keep track of, and the work to start something is equal to the work to stop it. So what we've discovered here is that work is the change in energy. In fact, this is what we call the work energy theorem. So the work energy theorem basically says that the work is the change in energy. And so if you do work on something, then you've changed its energy. Positive work adds energy, negative work takes energy out. Now, I will point out that this is what we call mechanical energy. We'll talk more about this later on here. We'll talk. Well, I mean, I guess you could do non-mechanical energy, but you do work on it, you put energy in. You if it does work on something else, energy goes out. As I mentioned in the live sessions, this is exactly backwards from how the chemists define it. But this is how physics and engineering typically does it.